Hello and welcome to Joey's Math. This is AP Precalculus lesson 1.5, polynomial functions and complex zeros. Today we have two lesson objectives. Number one, identify key characteristics of polynomial function related to its zeros when suitable factorizations are available or with technology. So we're going to learn what factorization is. We're going to learn what multiplicity is. We're going to learn what successive differences are. And we're also going to learn how to determine if a polynomial function is even or odd. So let's look at our first learning objective of factorization, where we're going to kind of review our concept from Algebra 2 of learning x-intercepts, zeros, roots, and linear factors. So if there is a polynomial function, like the graph here, if you can see from the graph has two x-intercepts. It has an x-intercept at -1, 0, and it also has an x-intercept at 1, 0. So we can say that these are x-intercepts of f of x. And if they are x-intercepts, we can also express that in equivalent terms. We can say that 1 and -1 are zeros of f of x. We can say 1 and -1 are roots of f of x equals 0. And we can also say that x minus 1 and x plus 1 are linear factors of f of x. So 0, root, linear factor, and x-intercepts are kind of the same thing, but used in different context. 0 is used in a context where an equation is given. X-intercept and 0 are used in the same context, but x-intercept is normally given in the coordinate form, whereas 0 is given in a numerical form. Linear factor is written in the format of x minus something. So these are all kind of same thing written in different formats. So yeah, make sure to know what the differences are. It's essentially the same thing, but they are used in different contexts. Now let's review what factorization is. So factoring techniques for polynomial functions include the following. For any number of terms, you can always try to factor using the greatest common factor. For instance, if you have 8a cubed b fourth minus 4ab, by looking at the expression, we can conclude that the greatest common factor is 4ab. So we can rewrite this as 4ab times parentheses minus a squared b cubed minus 1. We can also factor using different techniques. If you're given with two terms, you can factor using the formula for difference of two squares. You should know that a squared minus b squared is a plus b times a minus b. When it's a sum of two cubes, like a cubed plus b cubed, the formula for expanding that or factorizing that would be a plus b times a squared minus ab plus b squared. If it's difference of two cubes, a squared minus b squared, you can rewrite that as a minus b times a squared plus ab plus b squared. If you do not understand why these two are equivalent, try expanding this using the distributor property. If you expand this, you will be able to get this. Same for difference of two cubes. If you do not understand how this format gets into this format, try distributing using the distributor property. Then you'll be able to get how this long expression can kind of be shortened down to a cubed minus b cubed. Yeah, if you have three terms, you can factor it using the perfect squared trinomials. So if you have a squared minus 2ab plus b squared, that is a plus b squared. Again, you can try to expand this and you'll see how to get that. If it is a squared minus 2ab plus b squared, you can kind of write that as a minus b squared. For general trinomials, you can kind of factor it in the format of this. I'll explain how to do that soon. If you have four or more terms, the only way essentially you can factorize is using grouping. You're going to find that there are some like common kind of terms. Like for instance, ax plus bx share a common term of x. So you can kind of factor out x. For the third and fourth term, they kind of share y. So you can factor out y, right? So if you have x times a plus b plus y times a plus b, you can rewrite that as a plus b times x plus y, which is factorizing using groupings. If polynomials cannot be factored, we call those prime polynomials. It's essential that you acknowledge these vocabulary words because communication and vocabulary words are essentially important when dealing with mathematics. Now let's learn about polynomial division. So a polynomial can be divided using two methods, which are long division and synthetic division. So let's first learn about synthetic division because honestly, synthetic division is way easier. So first of all, you're gonna kind of write upside down division sign. And what you're gonna do is you're gonna write the coefficients of the dividends here. So the coefficients of the dividend is 2, 4, 1, 1, right? It should be in standard form. So the first coefficient here should be the coefficient of the highest degree term, so on and so forth. Now, here you're gonna write the zero of the divisor. If you think what the zero is for the divisor, it's 1. Because if you were to graph x minus 1, the x-intercept of x minus 1 is 1. Okay, from here, what we're gonna do is we're gonna first of all follow this kind of algorithm, which I have listed here. But essentially what you're gonna do is you're first gonna lower the coefficient of the highest degree term down. You're gonna multiply these two numbers, and then you're gonna write it here. So it's gonna be 2. And then what you're gonna do is you're gonna add these two. If you were to add those two, you're gonna get 6. And then what you're gonna do is you're gonna multiply this and this. And then just like how we did before, you're gonna write the answer that you get from the multiplication here, which is 6. And then you're gonna add 1 and 6, which will get 7. And just like how we did, we're gonna multiply 7 and 1. And then you're gonna write 7, which because 1 times 7 is 7. And then you're gonna add these two again so that you'll get 8 here. What does this tell us? This actually gives us a lot of information. Out of the 4 numbers written at the bottom row, the first 3 numbers tells us what the quotient is. Quotient is essentially the answer you get out of division. So by looking at the 3 numbers, the first 3 numbers written at the bottom row, we can conclude that the quotient of this division would be 2x squared plus 6x plus 7. Because there are 3 numbers, we're going to assume that the last number is constant. And then the second number is the coefficient of the x term. And the first term is the coefficient of the quadratic term. If you have 4 terms, you're going to assume that the first number is the coefficient of the cubic term. The second number is the coefficient of the quadratic term. The third term is the coefficient of the linear term. And the fourth term is the coefficient of the constant term. So essentially, we're able to find what the quotient is. Now, what's this fourth number indicate? This essentially indicates the remainder. So by doing synthetic division, we can essentially find what the quotient and remainder are in a really easy manner. There's one thing you have to note. If the divisor's leading coefficient is not 1, it is necessary to divide the quotient that you have obtained at the end of synthetic division by the divisor's leading coefficient. Okay, what is this talking about? So let's say that this entire division is actually 2x cubed plus 4x squared plus x plus 1 divided by 2x minus 1. So in this case, the divisor's leading coefficient is not 1. The divisor's leading coefficient is 2, right? So in this case, what we're going to do is we're going to do everything same. We're going to, first of all, write the coefficients. And we're going to find the x-intercept of this divisor, which is essentially 1/2. And then we're going to do everything same. 2, multiply these two. 1, 5, 5 over 2, 7 over 2, 7 over 4, 4 over 11. So we can conclude that quotient would be 2x squared plus 5x plus 7 over 2 and the remainder is 11 over 4. However, this is not actually the right answer. Because the leading coefficient is 2, it is necessary to divide the quotient that you have obtained at the end of the synthetic division by the divisor's leading coefficient. So essentially, instead of having 2x squared plus 5x plus 7 over 2, we're going to divide all terms by 2. So then we will be able to get, I'm going to write it down here, x squared plus 5 over 2x. And then we're going to have 7 over 2 over 1. So that would give us 7 over 4. So this is actually the actual quotient. So make sure that if the divisor's leading coefficient is not 1, when you're doing synthetic division, everything stays the same, but you have to make sure that the quotient is divided by the divisor's leading coefficient. If the divisor's leading coefficient is 3, you have to divide the quotient that you have obtained at the end of the synthetic division by 3. However, remainder does not have to be divided. So remainder stays the same as 11 over 4. Yeah, so that's essentially synthetic division, how synthetic division works. And make sure to know that synthetic division can only be used when the divisor is a linear expression. So if the divisor, which is this expression, is a quadratic expression or a cubic expression, it is not possible to use synthetic division. You can only use what is called long division, which I will be explaining in a minute. Great, so now let's learn how long division works. So long division works just like how we do numerical divisions. So if you think how numerical divisions work back in like elementary school, if you were to divide 27 by 2, what you would do is you're going to think of, you're first going to think, oh, how many 2's can fit into 2, right? And you can kind of think, oh, only 1 2 fits into 2. You're going to do like 2, and you're going to do like 7, and you're going to think how many 2's fit into 7? It's 3, right? So that's how kind of long division worked in elementary school, right? It's the same exact process, but with expressions and with like variables instead of just simple numbers. So I'll kind of go through how this process works. And long division is more complicated than synthetic division, but long division can be used where the divisor is not, where the divisor is like cubic term, quadratic term, quartic expression. So long division can be used for all types of polynomial division, whereas synthetic division is only exclusive to instances where the divisor is a linear expression. So how it works, I wrote it down here, but I'll just go through it with you again. You're actually going to write the actual division kind of symbol, and you're going to write the dividend here. You're actually going to write the entire expression, not just the coefficients. And you're going to write the divisor on the left side. And first of all, you're gonna think, just like how numerical divisions work, you're first gonna look into this the leading term of the divisor, and you're gonna think, how many x, because x is a leading term, how many x would fit into 2x cubed? In other words, what do we have to multiply 2x in order to get 2x cubed? Because we're trying to get 2x cubed out of x. So if you think about it, if you multiply 2x squared to x, then you will be able to get 2x cubed. So that's the first step. Now you're going to multiply 2x squared to our divisor, and you're going to write it below our dividend. Then you're going to get 2x cubed minus 2x squared. And just like how numerical divisions work, you're going to subtract the top expression and the bottom expression. Then you're going to get 0, and then because it's minus minus, it's going to turn into plus. You're going to have 6x squared. And if you lower this, you're going to get plus x. Just like how we did the first time, you're going to think, how can we get 6x squared from x. So how many x's would fit into 6x squared? Or in other words, you can kind of think, what would give us 6x squared when we multiply something to x? If you think about it, it's 6x. So if you multiply 6x and x minus 1, you will be able to get 6x squared minus 6x. If you subtract it just like the first procedure, you'll be able to get 7x plus 1. Why is it 7? Because we're distributing the negative sign due to the distributive property. So the negative here turns into a positive due to the distributive property. So it's going to give us 7x plus 1. And now you're going to think, what should we multiply to x in order to get 7x? It's just 7, right? So you're going to add 7 here, and you're going to multiply 7 and x minus 1. Then you'll be able to get 7x minus 7. And if you subtract it, you're going to get 8. So from this process, you can find that the quotient is what's given at the top. So quotient can be found to be 2x squared plus 6x plus 7. And remainder can be found to be 8, which is what's at the bottom. If the remainder is 0, what you get at the end would be a 0. However, in this case, because our remainder is 8, it is 8. So we kind of gone through how long division and synthetic division both work. It's highly, highly, highly essential that you know how these work because especially for long division, it is written as part of the AP Precalculus course and exam description. So it is imperative that you do a lot of practices in this area so that you are proficient of how to utilize long division whenever you face a polynomial division question. It's also useful to know synthetic division because synthetic division is an easier method to divide polynomials compared to long division. Okay, now let's learn some theorems. So first thing we're going to learn, which is from Algebra 2 actually, is the remainder theorem. So the remainder theorem states that if a polynomial f of x is divided by x minus a, the remainder is f of a. There's a typo, sorry. So what this is saying is that it's actually common sense. If f of x is divided by a linear term, the remainder is actually f of a. So you can find the remainder of a polynomial division by simply finding the 0 of the divisor and plugging it to our variable. So for instance, if you were to find okay, let's say that you have a polynomial of, let's say f of x is 2x cubed plus 4x squared plus x plus 1. And let's say that that is divided by x minus 1. Then the remainder from this process is simply f of 1. Shall we check? If you plug in 1 for x, you'll be getting 2 plus 4 plus 1 plus 1, right? That is 8. And actually, we did this entire long division process, and we also found that the remainder is 8, right? So essentially, another way of simply finding the remainder according to the remainder theorem is essentially by just doing like f of 1. That's essentially what the remainder theorem is saying. And as an extension to the remainder theorem, the factor theorem states that if a linear factor x minus a is a factor of f of x, f of a equals 0. And this is because if x minus a is a factor of f of x, the remainder when divided into 2 should be 0. So essentially, an easy method of finding whether something is a linear factor or not is by using the factor theorem or the remainder theorem. So essentially, let's say that the question is, they give you f of x like this, and the question's like, determine if x minus 1 is a linear factor of f of x, right? A really simple way of checking is by doing f of 1. Because if f of 1 is equal to 0, it means that the remainder that you get out of the polynomial division is 0. So if f of 1 is equal to 0, according to the factor theorem, that proves that x minus 1 is a factor of f of x. However, in this case, f of 1 is not 0. It's actually 8, right? As we have found. And this also shows that according to the factor theorem, x minus 1 is not a linear factor. Because if x minus 1 were to be a linear factor, f of 1 should equal to 0 by definition of the factor theorem. So factor theorem is an easy and the best way to determine whether a linear factor, or not even preferably a linear factor, is an easy way of finding if a linear factor is actually a factor of the polynomial that is given. So essentially, that's a really simple way of kind of dealing with remainder theorem as well as factor theorem. Now let's learn about complex conjugate theorem. So complex conjugate theorem states that if a complex number a plus bi is a root of a polynomial equation, a minus bi is also a root of a polynomial function. So for instance, let's say that the question tells us that 2 plus I is one of the factors, right? Then according to this complex conjugate theorem, 2 minus I is also a factor. Some people question me, why though? Why? The answer is because all polynomial functions given in AP Precalculus examination, the coefficients are all real numbers. For instance, if you're given like a really complicated polynomial function, this is actually not complicated, but if you're like something, let's say that you're given a random polynomial function like this, right? All the coefficients are always in the real number system. You will see 0 question that has like a coefficient with a imaginary number. That's not going to appear within AP Precalculus at all. So because all coefficients are real numbers, it's impossible to have a single complex root. Therefore, if a plus bi is a root, a minus bi should also be a root, because if they are conjugates, if you multiply them, the imaginary part actually goes away because I squared is defined as -1. So in order to get rid of the imaginary number, this complex conjugate theorem works in a way that if 2 plus I is one of the factors, 2 minus I is also a factor of f of x. As an extension, this also works for like irrational numbers. There may be some instances where actually not. For all polynomial functions, preferably, all the coefficients would be rational numbers. So there won't be instances where something's given like this. I don't think that's gonna come up within the scope of AP Precalculus. Therefore, unless the equation is something random like this, normally everything's gonna be rational numbers, meaning that all the coefficients will be numbers that can be expressed in fractions. So in that case, because there are no irrational numbers within the coefficients, it also tells us that if a plus b root c is a root of a polynomial expression or an equation, its conjugate should also be a root, so that when we multiply those two, the irrational number can go away and we can only have rational numbers. So the same logic works for both complex numbers as well as irrational numbers. So essentially, if you have a root with an imaginary number in it, its conjugate should also be a root according to the complex conjugate theorem. And the same thing works for irrational numbers, because all polynomial coefficients should be rational numbers. If you see a root with an irrational number in it, its conjugate should also be a root. Yeah. Great. Now let's kind of learn about technology, because AP Precalculus highly emphasizes the use of technology. In this textbook, we're only utilizing the usage of TI-84. So if you have other calculators like TI-83 or even TI-Nspire, there are similar features to this polynomial finder in your calculators. So I highly recommend searching up on YouTube. But due to the time constraints we have, I will only go over TI-84. So the graphing calculator can be used to locate the exact real zeros of a polynomial function by locating its x-intercepts, which can be useful to confirm or check your estimate. So first of all, how to find x-intercepts? You're going to enter the function. So in the y equals this, if you take a look at your TI-84 calculator, there would be a y equals kind of button at the top of your calculator, top left. Click that and enter the function that you have, and also enter y equals 0 so that you're simulating the x-axis. And then you're going to graph the function. How are you going to graph the function? First, you're going to click the graph button, and then you're going to click zoom button. How can you click zoom? Zoom is located on the top middle. So you're going to click zoom, and you're going to scroll down and find 0 column zoom fit. Then the graphing menu will kind of show those two graphs that we have in kind of a closer look. And then you're going to use the calc menu. How can you use the calc menu? You're going to click second and the blue button, and you're going to click trace. Second trace is calc. So if you click calc, there will be a function, there will be a feature or an option where you can find the intersection point. So if you were to find the intersection point of the function and the x-axis, that's essentially what x-intercept is by definition. And you're going to move the cursor closer to the x-intercept point. Preferably, the first cursor should be below the x-intercept point, and the second cursor should be above the x-intercept point. And if you press enter 3 times, the calculator will automatically locate you to what the x-intercept point is. So that is a very useful way of finding the x-intercept or root of a polynomial equation if you were to find it. But this is more like visual stuff. It kind of tells you visually where the x-intercept is. If you're kind of running out of time and if you want to just find roots in a very, very simple way, or if you want to find polynomial functions like complex zeros as well, you cannot use the x-intercept feature because x-intercepts for roots that are real numbers, those can only be shown within the Cartesian plane. So in order to find polynomial functions complex zeros, like imaginary zeros, you have to use a feature called polynomial root finder. So you're going to use apps menu. There's a feature called apps. It's below mode and xt theta n. So if you click apps, and if you scroll down and click 9 colon PLYCSMLT2, and if you click enter, and then if you click 1 colon polynomial root finder, there'll be a bunch of features. You're going to adjust the order as the polynomial's degree. So if the polynomial is a quadratic polynomial, you're going to set the order as 2. If it's cubic, you're going to set the order as 3. And you're going to adjust the number system to a plus bi so that it includes complex zeros. Even if you're only finding real zeros, you can still have it to x plus bi's, because if the polynomial function only has real zeros, that's all what's going to show you. And then you're going to click next by clicking the graph button. The graph button is located on the top right corner. And you're going to fill out the polynomial function and click solve by clicking graph. Then this amazing feature will automatically find you all the roots of the polynomial function, whether it's a complex zero, real zero, or whatsoever. I wanted to emphasize though that you may only use a graphing calculator for questions that explicitly mention you may use a graphing calculator in this textbook. In the AP exam, there would be a graphing calculator required section and a non-calculator section in both MCQ and FRQ. So for a graphing calculator required section, I believe that it is useful to know these two methods of polynomial root finder as well as locating the x-intercept, because it does save you a lot of time. Because if you don't know how to do this, the only way you can find zeros of a polynomial function is through factorization, which takes you a lot of time. So if it is a graphing calculator required section, or if the question in this textbook says you may use a graphing calculator, do utilize these functions. It does save you a lot of time. Okay, due to time constraints, I'll only solve example 5. And then all the other questions can be kind of self-explanatory. So let's go on. So first of all, we have example 5 question, which reads as use a factor theorem to determine if the binomials given are factors of f of x. Use the given binomials to find other factors of f of x to write a complete factored form of f of x. So first of all, let's check if this factor x plus 10 is a factor of this polynomial. We can check that by using the factor theorem by plugging in minus 10 to x, because minus 10 is a root of x plus 10. Then we're going to have minus 10 to the power 4, minus 10 to the power of 3, plus 9 minus 10 to the power of 2, plus 58 minus 10, minus 16. Then we're going to have yes, then we're going to have 20,304. So this is not a factor. Yeah. Next, what we're going to do is we're going to check if this is a factor of this. But noting that the polynomial function does not have any irrational numbers, we're going to use the conjugate theorem. So if this is a factor of this, then also its conjugate is also a factor. So if you were to multiply these two, what we can get is we can get x squared minus 2x minus root 3x minus 2x plus 4 plus 2 root 3 plus root 3x minus 2 root 3 minus 3. So cancel off, cancel off, cancel off, cancel off. We're going to have x squared minus 4x plus 1. So essentially, we found the potential factor candidate for this polynomial by using the conjugate theorem and by multiplying the conjugates. So yeah, from there, we can find if, however, there is a possibility that this might not be a factor of this polynomial. So we have to double check. How we can double check is we can do a long division. So if you were to do a long division with our f of x as our dividend and our factor that we have obtained as our divisor, I'm going to skip all the steps. We actually get x squared minus 6x minus 16. So because the remainder was 0, it does show us that this is a factor of f of x. So let's say that. And for other factors, to find a complete factored form, we can rewrite f of x as x minus 2 minus root 3, x minus 2 plus root 3. And then if we were to factorize this, that would be x minus 8, x plus 2. So that would be our correct answer. So by doing this kind of complicated procedure with all the long division and stuff like that, we finally obtained that f of x can be rewritten into factored form like that. Great. Now let's learn about the concept of multiplicity. So first of all, repeated zeros occur when the polynomial's linear factor has an exponent of a number more than 1. So for instance, in this polynomial, because for the linear factor of x minus 1, the power of the linear factor is 2. So we can conclude that this polynomial has a repeated zero at has a repeated zero of x equals 1 as the linear factor of x minus 1 has an exponent of 2. So essentially, if the exponent of a polynomial is 2 for a linear factor, then at that point, there is a repeated zero happening. When dealing with repeated zeros, a graph's behavior can be predicted by looking at the linear factor's exponent, also known as the multiplicity. So essentially, the exponent of the linear factor is called the multiplicity. So for a function with a linear factor, x minus c to the power of m, where c is a zero of the function with multiplicity exponent of m, if a zero c has odd multiplicity, the graph crosses the x-axis at x equals c, and the value of f of x changes its sign. If a zero c has even multiplicity, the graph does not cross the x-axis. It bounces off. It is tangent to the x-axis at x is equal to 3, and the value of f of x does not change its sign. So what this is saying is, if you take a look at this example, for the linear factor x plus 1, because the exponent of this linear factor is 3, the root x is equal to -1 has a multiplicity of 3. And because it has an odd multiplicity at x is equal to -1, the function crosses the x-axis. If you take a look at this, the function passes through the x-axis, right? So the graph changes its sign from negative to positive because there's an odd multiplicity happening. However, if you take a look at the other example or other linear term here, this linear term has a multiplicity of 2, right? So because it's an even multiplicity, at x is equal to 1, the graph does not cross the x-axis. It bounces off. It bounces off. So the sign does not change. It's still positive, and the graph does not cross the x-axis. It just bounces off. So multiplicity is a great way to determine the behavior of the graph. Now let's learn about the fundamental theorem of algebra and corollary to the fundamental theorem of algebra. So fundamental theorem of algebra states that a polynomial function of degree n, where n is greater than 0, has at least one zero, real or imaginary, in the complex number system. Corollary to the fundamental theorem of algebra states that a polynomial function of degree n has exactly n zeros, including repeated zeros, in the complex number system. So for instance, what this is saying is if we have a quartic function, this has to have 4 zeros. However, these 4 zeros can include repeated zeros, as well as complex zeros. So for instance, for the function y is equal to x is x to the power of 4, this function has only one zero. The only zero is 0. Why? Because there's a repeated 0. Because this linear factor has a multiplicity of 4, there's a repeated 0 of 0. There are 4 repeated zeros. So you can essentially kind of predict the number of zeros available according to the corollary. It's the fundamental theorem of algebra, because if a polynomial function has a degree n, it means that it has exactly n zeros, including repeated zeros as well as complex zeros. Let's also try one question. Let's try example 7. Determine the zeros and state the multiplicity of any repeated zeros for f of x is equal to 4x times x to the power x plus 3 to the power of 2, 3x minus 1 to the power of 3. Explain the result using corollary to the fundamental theorem of algebra. Okay, so we have, what zeros do we have? We have 0 from this factor. We have -3 from this. And then we have 1/3 from here. This multiplicity is 2. and 1/3. Multiplicity is 3. So essentially we have, including repeated zeros, we have 6 zeros total. And if you think about it, there's 4x here. And if you just consider the greatest term, it's going to be x squared. And then for this, it's just going to be like 27x cubed, right? So if you multiply these all together, you're going to get something x to the power of 6. So it does match. According to the Corey fundamental theorem of algebra, the leading coefficient or the leading term of this function would be 108x to the power of 6, according to the Corey to the fundamental theorem of algebra, because the leading term has a degree of 6. It is logical to think that including the repeated zeros, there are 6 zeros total. So it does match to our result shown in the Corey to the fundamental theorem of algebra. Great. Now let's go over our, is it our last concept? No, right? Our second last concept of successive differences. So in lesson 1.3, the concept of first difference and second difference was examined by looking into linear sequences and quadratic sequences. I don't think it was covered in the videos, but definitely check out the textbook if you were, I'm gonna go over it today. So certain successive, I'm gonna explain what successive differences are in the first place. Successive differences are differences between the successive terms and the current terms. So for instance, their original term like this, right? For this table, this table has equal interval input values. So we can conclude that the terms are 6, 11, 18, 27, and 38. If you calculate the difference between consecutive terms, you can find 5, 7, 9, and 11. That's called the first differences. And if you were to find the difference of the first difference, you'll get 2, and that's called the second difference. So like these are what's called like successive differences. You're finding the difference of the difference essentially. So certain successive differences are constant depending on the degree of function. So for linear functions, the first differences are constant. So no matter what data tables are or data values are given, if you calculate the first difference, they would be all same for linear functions. For a quadratic function, the second differences would be constant. So if you take a look at this example, the second difference is constant, right? The second difference is all 2. Therefore, we can conclude that the function has a degree of 2 as the second difference is constant. This is a valid argument because it is defined that quadratic functions, for quadratic functions, the second differences are constant. For cubic functions, therefore, the third differences would be constant. Thus, the degree of a polynomial function can be found by examining the successive difference of the alpha values over equal interval input values. So if successive nth differences are constant for a polynomial function, the polynomial function would have a degree of n. So calculating the successive differences is an effective way of calculating or determining the degree of a polynomial function. Let's solve one example. So let's look at example 13. So if you take a look at this, okay, so we have points, but make sure to know that they are not equal intervals. If you take a look at this, there is 3 here, which can be ignored because 3 is not an equal interval. However, 0 to 2, 2 to 4, 4 to 6 are an equal interval. So we're just going to disregard this point, and we're going to use the other 4 points. So if you just take a look at the y coordinates, we're going to have 4, 48, 164, and 352. If you calculate the first difference, we're going to have 44. And then we're going to have 116. And then we're going to have 188. If we calculate the second difference, we're going to have 72. And then we're going to have 72 as well. Therefore, because the second difference are constants, Because the second differences are constant, we can define that this unknown polynomial function has a degree of 2. Great. If they ask you to explain your reasoning like verbally, you have to explain that because the second differences are constant by having a value of 72, therefore we can conclude that the degree of this unknown polynomial function is 2, or in other words, it's a quadratic function. Now let's look at our last LO of odd and even functions. The functions that are symmetric with respect to the origin are called odd functions. Odd functions are in the form of f of x is equal to ax to the power of n, where n is a positive odd number. So for instance, if you take a look at this, f of x is equal to x. This is also written as x to the power of 1. So because 1 is an odd number, this function is an odd function. Some features, some algebraic definition of odd function is that f of negative x is equal to negative f of x. So for instance, if you take a look at this example, f of negative 2 is negative 2, right? Negative f of 2 is also negative 2, if you take a look at this, because f of 2 is 2, negative f of 2 is negative 2. Because f of negative 2 is negative 2, we can conclude that f of negative x is equal to negative f of x for odd functions only, as proven with this example. So if an unknown function follows this algebraic definition, we can conclude that that is an odd function. For even functions, a function is an even function when it is in the form of f of x equals ax to the power of n, and where n is a positive even number. So if you take a look at this example, 2 is an even number, so this is an even function. The algebraic definition of even function is that f of negative x is equal to f of x. So if you take a look at this example, f of negative 2 is 4, and f of 2 is also 4, because there's a symmetry with respect to the y-axis. For odd degree functions, there's a point symmetry with respect to origin. So for odd degree functions, there's a point symmetry. And for even degree functions, there are line symmetry. Great. Okay, let's look at example 16. Yeah. Graph the following function using a graphing calculator. You can do that part. Analyze the graph to determine whether the function is odd, even, or neither. So if you can take out your graphing calculator, and if you graph this, make sure to click zoom fits so that your graph shape fits into your calculator. Sometimes it may not work, then you can try and zoom standard or zoom square. Okay, so if you take a look at the function graph on the graphing calculator, there's a point symmetry. And because there is also 3, which is an odd number, I'll assume that it's an odd function. We can confirm algebraically though. The algebraic definition of odd function is that f of negative x is equal to negative f of x. So let's confirm. In this case, it's not f, it's h. So let's check if h of negative 2 is equivalent to negative h of 2. H of negative 2, if you plug in, would give us negative 8 plus negative 8 plus 6, which is negative 2. Negative h of 2, if you plug in 2 to x, would give us 8 minus 6, which would give us -2 as well, because there's a negative here. So because this definition of odd functions fits when we plug in x is equal to 2, we can confirm that h of x is an odd function. So we can say that is an odd function. And we can write the definition as because h of negative x is equal to negative h of x. And we can also say that there is a point symmetry with respect to the origin. That will be a perfect answer that gives you all the points for an FRQ. Great. I think that is it for lesson 1.5. That was a long lesson. Thank you so much for listening. Yeah, so essentially you will be comfortable now with factorization, multiplicity, successive differences, as well as determining if a polynomial function is even or odd. Thanks so much for watching. And if you have any questions, feel free to email me. And yeah, thanks for watching.